Hi, in this video, I'm going to cover topic 2.8, which is the least squares regression. Some learning objectives. We want to estimate parameters for the least squares regression line model. Okay, so that would be like the slope and the intercept of that line. And we want to interpret those coefficients. Right? So what does the slope tell us about the relationship between the explanatory and response variable? What does the intercept tell us? Okay. Now in this video, we're not going to really get into all that. I just want to present some kind of conceptual understanding of the least squares method. All right, so let's start with this question. How do statisticians find the line of best fit? After all, right, there's many possible lines we can draw through a scatter plot. Okay? So here I have a scatter plot showing foot length versus height. And I've created like 6 different lines. Okay, some seem to be pretty good fits and some seem to be pretty poor fits. So how do we know which line is the best? Are any of these 6 lines the best, or is there one that's better than these 6? So what we'll do is, we'll use an applet to kind of explore this. Okay. So here is foot length versus height. And what we can do is we can put in a line, right? And we can, move this line any which way we want. Okay. So, I might think this is the best line, but how do I really know if it's the best line? Okay. Well, what statisticians have come up with is a way of measuring variation here. And so we could look at the residuals, right, between our data points and the line. And you can see for this horizontal line, there's some big residuals. Okay. But instead, right, what we're going to do is we're going to look at the squared residuals, right? And we're going to add those up. Okay. Think about why we don't add up the residuals, right? Some residuals are positive and some are negative. So when you start adding them up, they're going to cancel each other out. Okay. But squaring makes everything positive. Okay. And it also gives us a nice visual representation, right, of area, right? The more area there is, the worse the fit, right? The more space that these squares take up, the poorer the fit. Okay, so this horizontal line does not fit the data very well. Let's see if we can do any better, right? So what I'm going to do is I'm going to keep my eye on this number down here, right? This number is telling me the sum of all those squares, right? The sum of the squared residuals. And so I want to try to make the squares small. And I can accomplish that by trying to get the line as close to the points as possible. Okay. Now we'll never be able to get it onto every single point because there is scatter. It's not like the points are perfectly lined up, but we'll try to do our best. Okay, so I'm looking at that number and I got it to 239. Okay, so that was just by shifting the line up and down. All right, let me play with the slope a little bit. Okay, so it looks like I'm getting it to about 235. Okay. All right, so this appears to be the line of best fit. It's the line that minimizes the size of those squares, the sum of those squares. Okay. All right, so do we have to find it by hand every time? No, we don't. Software can determine where the line of best fit is for us. Okay, so now it's showing us the red line is the line of best fit, and we can check, and yes, the sum of the squared residuals was 235. I don't know if it would have saved mine. No, it didn't save what I had, but that's it. Okay, here's another neat little fact about the least squares regression line. If you have any scatter plot and you create the least squares line, it will pass through the average x value and the average y value, always. Okay. So no, I didn't just get lucky here. I'll make another scatter plot. Okay, there's the regression line, the least squares line. And again, it passes through the average x and the average y value. Okay. All right, so let's return to the slides. Okay. So the least squares regression model will minimize the sum of the squares of the residuals. Okay. So on the left, I kind of have like that baseline, right? So just a horizontal line where the squares are pretty large, okay? And then on the right in red, we have the least squares line. This is the one that minimizes the sum of the squares. All right, we mentioned how the least squares regression line will always pass through the average X and Y coordinates. Okay. And then now I want to look at, how good is this regression line? And another way of asking that is, well, how much variation did it actually remove? So if I start with the blue graph as kind of a baseline, okay, that's just a horizontal line. In fact, that horizontal line is positioned at the average height for the data set. Okay, I know I started with about 475 units worth of variation. Okay. And then the red graph, right, shows us the line of best fit, where we were able to reduce the variation down to about 235 units. Okay. So how much variation were we able to remove? Well, 475 minus 235 means that about 240 units of variation were removed. Okay, well, the units, I guess the size of this number kind of depends on, the scale here on the X and the Y axis, okay? Mainly the Y axis. So a better question would be, what percent of variation was removed? Okay. So I was able to remove 240 units of variation, but I started with 475. So if I create a ratio, right, then that shows me about 50% of the variation was removed. Okay, not bad, not too shabby. Now, turns out that there's an easier way to calculate how much variation was removed. Okay, and it has to do with the correlation coefficient. Okay. So the correlation of this particular relationship is 0.711. Okay. But if we square that number, right, if we calculate R squared, it's 0.506, which is the exact number we calculated for the percent of variation removed. Okay. So it's not really necessary to, have to figure out how many units of variation we start with and how much units of variation are left, and to do all these subtractions and forming ratios, right? You can simply just get the correlation coefficient, square it, and then that tells you how much variation is removed. Okay. Obviously, if we can remove 100% of the variation, that would be great. But realistically, that's very hard to accomplish. Okay. All right. So R squared, right? The correlation coefficient squared measures the proportion, the fraction, the percentage, right? Whatever word you prefer, of variation in the response variable that is removed or that is explained by the explanatory variable in the model. Okay. So for this particular data set in this context, we could say that about 50.6% of the variation in height is explained away by having foot length in the model. All right, so that concludes this video. In the next video, I'll demonstrate how to find the slope and the intercept of that least squares regression line.